I want to extend the idea from the last few videos to a third order differential equation. In this case, my characteristic equation looks like r cubed plus 3r squared minus r minus 3 equal to 0. And we can factor this by grouping. If I look at my first two terms, they have an r in common, or an r squared in common, and I'm left with r plus 3. My next two terms have a minus 1 in common, and I'm left with r plus 3. We can now factor out the r plus 3. I'm left with r squared minus 1. And that term factors further into r plus 1, r minus 1. So here my values of r would be -3, -1, and 1. So my solution would be of the form c1 e to the minus 3t plus c2 e to the minus 1t plus c3 e to the 1t. So this does work for higher order derivatives or higher order differential equations as well, as long as you are able to factor this or figure out what the roots of that polynomial are. Let's consider the case of a third order differential equation where I know two of the roots are the same but the third one is different. So how would I write this solution? Well, we have c1 e to the r 1t plus c2. When we dealt with second order differential equations, if we had a repeated root, we included a factor of t, so that's what I'm going to do here. For that second root, that is the same as the first one, so these two are the same. And since the third one is not the same, I no longer need the factor of t there. So here would be my solution. What about the case where they're all the same? Well, in this case, I'm just going to call them all r. So I would have c1 e to the rt. c2, I would include the factor of t, since we have it repeated. And c3, since this one is repeated again, this time I'm going to include another factor of t, so t squared e to the rt. And we can see how this idea might extend to higher order differential equations with repeated roots.